Okay, welcome back to the next part of the video. In the last video, we got ourselves all fueled up and ready to go. We've got all the locks that we need to make it all the way through the mission. And we did a few basic calculations to make sure that we would in fact have all the fuel that we needed for the entire mission. So now we're ready to fly. But what we got to do here first is we need to get closer to the launch date, because while we were setting up our plan, we decided that we would leave one day later than we actually set up. So let's go to stage 2 here, and let's get a look at when that eject date is. That's 5794.1362. So let's go ahead and warp time ahead, get closer to that point. Let me make sure I've got external cooling on. Okay. That's 1, 2, 3, 4, 5, 6, 7, 8. Let's back time down a little bit. Getting pretty close. And we want to leave ourselves enough time to get up into orbit. One thing I want to figure out real quick, just give me 1 second here. I want to figure out how much time. So I'm going to put in this number, 57594.1362. And that's going to be obviously July 25th at 3, we'll call it 3:16, and we want to know what it is right now, because basically what I want, actually what I can do is I'll do it this way. I basically want an hour, roughly an hour, so let's just put in 2 here, and we'll warp time ahead until we're at about close to this time. That way that'll be 1 hour before the eject date, so that'll give me about an hour to get up off the landing pad and get into orbit. And that was 57594.0945. And we're getting pretty close. 0809, we'll go with that. Okay, now we need to go back to stage 1 now that we've warped time ahead, and we just need to get everything dialed in, because obviously the eject orientation that we established yesterday is no longer valid, even though it's really not that far off. And we really won't even need an hour like I thought, because we're not going to go. The reason I wanted an hour, because I figured if our eject, or if our launch date was over, if we were going to launch from this point and have to go all the way around, we would need close to an hour. But since we're launching here, it looks like we're only going to need maybe 25 or 30 minutes. So let me go back here and let's go forward another, let's just go forward another 20 minutes. So we'll bump the clock forward to 1084. Alright, that's close enough. Okay, so we're going to have a heading of about 62 degrees. Let's go ahead and turn the APU on. Let's get everything zeroed out here. Turn on rotation. Don't need the retro doors open. And we'll bring up orbit MFD on this side. Change the projection to the ship. Use the distance readout that's above the surface and the equatorial frame. Hover doors are open. Turn off external cooling.
Using onboard O2.
And let's hope we're not forgetting anything. If we are, we'll stop at a convenience store and buy it along the way. Alright, here we go.
Wheels up. Gear up. Gear up and locked.
Okay, now we're going to rotate. Actually forgot the heading I needed. That's not very good. We'll use the relative inclination to figure it out. And full throttle on the main engines. Kill the hover. Close the hover doors. Engage the attitude hold. And we'll just keep an eye on our relative inclination to make sure that it's making sure that it's going down.
Mach 2. Mach 3.
And we won't get up too far before we'll level out. Martian atmosphere is so thin, you don't have to get up to, 60 kilometers or anything like that.
Mach 4.
And we've got a pretty good climb, so I'm going to go ahead and just zero out now.
Mach 5.
And I'm watching the white line here. Just going to make an adjustment, bring that around to our current location.
Mach 6.
And relative inclination is creeping down a little slowly. That's still good. Apoapsis is showing 25 kilometers and
Mach
climbing.
7.
Relative inclination coming down, so we're looking good. Everything here is right where we need it to be.
Mach 8.
And we burned through our fuel module, so we'll be able to dump that once we get up
Mach 9.
and kill the main engines. That'll save us 355.2 kilogram of mass, and that'll increase our overall DV. Science.
Mach 10.
Watching the relative inclination.
Mach 11.
And we're going to pitch up a little bit.
Mach 12. Mach 13.
I'm just trying to slow down the relative inclination. I'm just not sure if I'm going the right way with it.
Mach 14.
Because you see, we're going to overshoot and go the other way. Okay, there we go.
Mach 15.
Okay, I'm just watching the apoapsis now.
Mach 16.
And there's 200 kilometers. Yeah, we didn't really get up quite as high as I would have liked, but that's going to be okay.
Translation.
Rotation.
Pitch.
The elevator trim's causing the nose to settle down, so I'm going to go ahead and turn surface controls on because we're still low enough in the atmosphere that we're getting a little bit of effect from the atmosphere, so I want to have the elevator set level so we'll stop pitching down like that. Okay, and we'll have just a little bit of work to do to get our relative inclination right where we need it, but we've got a pretty good, that's pretty low, 0.013, and it's actually going down a little bit because we're still getting a little bit of effect from the atmosphere. I believe I'm going to wait a little bit on the radiator. Let's check my dynamic pressure. And we're okay. And I'm also going to jettison that spent fuel module.
Translation.
Rotation.
Mach 16.
This climb up through the atmosphere wasn't the greatest. I should have been pitching up a little bit more, up for a little bit longer, that is. But it's okay. I mean, all right. So we're gonna jettison that,
Payload deployed.
and we can just see what's happening there. And warp time ahead a little bit, and then that'll go around and crash into the ground. Let's close the payload. And now if we look at burn time calculator, since we got rid of that, we have an accurate estimate total for our DV. Okay, now let's go ahead and turn the APU off now that we're done with all that. Switch over to orbit HUD. Now we got to circularize and head out to Venus. Although actually, we're going to reach apoapsis in 800 and some odd seconds. And we're burning, yeah, okay, we're going to need to circularize. And let's go prograde. And what I can do here is I'm going to bump the translation a little bit.
Translation.
Just to bring that relative inclination down. There we go, that's probably as low as that'll get. You can see how quickly that spins around as I try to get it over top the current location. That just is an indicator that it's really low. Alright, now what I want to do is a couple of things. There's actually a way to improve your eject. We're saying, according to Transx, we've got it set up saying that we're going to eject here at 57594.1362. But according to stage 1, we're going to reach the ejection point at this number, which is the same thing, but it's 1570. It's a little bit later. So what I want to do, in order to improve the accuracy of everything, is I'm going to set this eject date to that number, which again was 1570. And now, of course, that will skew all my, plan, but it's actually going to be more accurate. So what I can do, now that this is all skewed a little bit, I've got time before I get over to apoapsis, and I've got time before I get over to the eject point, is I can now tweak this plan a little bit now that I'm in orbit. So we'll go forward on this side. We just want to bring that relative inclination down. Okay, it looks like we're going to need just a little bit of prograde to help us out. And that's pretty close right there. Let's see if we can get just a little bit more correction on the relative inclination. Yeah, that's looking really good there. So that's our Venus sling. And if we come forward to our Earth encounter, we can see that it's now out a little bit. So what we can do is go back to, or go forward to stage 4 here, and we can work with our outward angle and relative and inclination angle a little bit. And again, these shouldn't be very large at all. Just a few clicks. And there we go. Now, of course, that's going to have a slight effect maybe on this, but it was very minimal. But if we wanted to, we could go to stage 3 here and stage 2 on this side and maybe just do a small tweak with the relative inclination like that. And now we're about as accurate as we can be on that, and that won't have really any impact or much on that stage. So now our plans, now that we're in orbit, we're just making a few tweaks to our plan to improve it a little bit. Not absolutely necessary, but I do feel that it's worth it. Okay, so that's set up. Now let's go and see also, since we changed the timing on stage 2, we changed the eject date a little bit. So let's see if we need to do anything with the relative inclination here. So we'll swing our white line around to our current location like that, and you can see relative inclination's a bit out, so let's improve that a little bit. Let's make sure we're prograde. Keep an eye on the apoapsis timing. We still got quite a little bit of time. And we'll bump the translation. And let's bring that back around. And there we go. So we're perfectly in plane now with the eject point. And according to, TransX, we've got a really clean line up here. So as long as our ejection burn is good, then we shouldn't have too much variation here, although it will drift a little bit, especially as we're pulling away from Mars because the gravitational permutations that TransX doesn't account for. But nevertheless, we should have a really clean plan here. Alrighty. Now let's go ahead and warp time ahead until we're at the apoapsis so we can circularize. And just to keep things nice and clean, let's let burn time calculator circularize the orbit for us. So we press MD to get over to time to apoapsis, and then we hit the circularization button, and it's going to do that burn in 346 seconds, and it's going to be a 10-second burn. So we're going to warp time ahead until we're close, and then we're going to go prograde. Okay, we're getting really close. Burning here in just a few seconds. Okay, we can turn prograde off. I can see our APA and PEA is just a little bit higher than what we had originally planned for back here in stage 1, but I don't think it'll be enough to matter. So now we're going to warp time ahead to get over here to the ejection point. And if I understand, if I did it correctly, then we should be at the ejection point at exactly .1570. So when the date here, the MJD, is .1570, that's when we should be doing that burn, right around that time. So let's warp time ahead to that point. And then once we complete the ejection burn, we'll be done with this part of the video, and then we'll pick it up in the next part. Just take a look real quick. 1405. And we still got some time, so I'm not sure if this is going to be exactly correct or not. I'm trying to learn how to get this eject date at exactly that point, and it's kind of tricky. It's almost impossible to get it set up while you're on the ground. I haven't figured out how to do it while on the ground. 1411. Yeah, it's going to be really close. I don't think it would ever be exact because you're going to start the burn. Basically, I think we'll hit this number 1570. I think we'll hit it when we're halfway through the burn, I think. Alright, let's go prograde. and when we're right about to begin the burn, we'll turn off prograde. Burning now. Okay, so we started the burn at 1423 instead of 1570, so I'm curious when we actually hit that 1570 point. I'm guessing it's when we're halfway through the burn.
Rotation.
Switch over to rotation and keep an eye on the semi-major difference. And I'm going to rotate inward just a little bit. To help bring that semi-major down a little faster. And I'm okay, we're at 1431. Now, it definitely won't be during the burn because 1570, that's like more than 14 minutes from now, so anyway. I'm going to start rotating back the other way because our semi-major is getting close to 0. I'm just doing a very small amount of control thrust to get the vessel yawing a little bit outward, trying to keep up with the amount of reduction in the semi-major so that it comes down basically at the same rate that we're losing delta V. So basically when the delta V reaches 0, I'm hoping to have the semi-major difference at its lowest point. It's actually starting to go up, so we need to go the other way a little bit. Okay, we're getting pretty close to the end of the burn. Yeah, our time is nowhere really even close to that eject date. Oh well, I've still got some work to do to figure out how that part works. Coming up on the end of the burn. Okay. Not too bad. Let's go ahead and finish this up. So we're going to translate the semi-major. Really nice.
Rotation.
Now we're going to do the same thing with the relative inclination.
Translation.
Just a bit of up-down. And there we are. You can see the white lines right over our current location, and the relative inclination is, some fraction of a small number.
Rotation. Translation.
Just a little bit left on the delta V. And there we have it. Okay, all of our numbers look good. We've got the semi-major down as low as I think I can possibly get it. Same with the relative inclination, and the delta V is the same. So we had a really clean burn. Burn completed roughly around 1450 according to that. So we didn't quite catch the eject date. I'm really curious to figure out how to figure that out, where you can get this set at the right time for the eject date. And the reason you want that, the reason I would like to have that anyway, is because of all these later stages. If you do because according to Transx, this is when we're going to do the eject burn, and since I did it a little bit early, then all of this is going to now drift a little bit more than it would otherwise. Don't get me wrong, this is all going to be extremely close, but it would be even more accurate if I could get that eject date exactly correct, and unfortunately I've just yet to figure out how to do that. Now there is another way to do Transx altogether. When you do these burns, you can set up a maneuver. I do that sometimes when just going to Mars or coming back to Earth, but when doing these slings, I'm not quite sure how you would do a maneuver, because I think you would lose all your later stages. Because in order to set up a maneuver back here for stage 2, what you end up doing is resetting your variables, and anyway, that's just a whole other video altogether. So that's going to go ahead and conclude this part of the video. Let's just quickly take a look at where we're at. We've been gone from the Olympus for 56 minutes, and according to Burn Time Calculator, we have 5,520 meters per second worth of delta V left, and that's really close to what I said it would be, because you remember this number is a result of subtracting away the all the encounter velocity. So if you remember, I said we would have, it was really close to this number. In fact, if you rewind the video, you can find out exactly what I said and how I came up with that. So, alright, that's going to be it for this part. Sorry if I'm rambling a little bit here at the end, but I'm just trying to explain a lot of stuff here. When we come back in the next part, we're going to be right here at Mars, and we're just going to warp time ahead to get over to Venus. Obviously, we'll do 1 or 2, maybe 3 mid-course corrections along the way, and it won't take long at all to go from Mars to Venus. It's not like going to the outer planets where it takes 20 minutes of time warp. So we'll be able to maybe even go from Mars to Venus and Venus to Earth all in one video. We'll see how it works out. If you like this video, leave a comment down below. If you have any questions about anything I did, or if you have any tips, advice, let me know. I always like to hear from people. See you in the next part. I want to figure out how much time. So I'm going to put in this number, 57594.1362. And that's going to be obviously July 25th at 3, we'll call it 3:16, and we want to know what it is right now, because basically what I want, actually what I can do is I'll do it this way. I basically want an hour, roughly an hour, so let's just put in 2 here, and we'll warp time ahead until we're at about close to this time. That way that'll be 1 hour before the eject date, so that'll give me about an hour to get up off the landing pad and get into orbit. And that was 575940945. And we're getting pretty close. 0809, we'll go with that. Okay, now we need to go back to stage 1 now that we've warped 6-2. So let's go ahead and warp time ahead, get closer to that point. Let me make sure I've got external cooling on. Okay. That's 1, 2, 3, 4, 5, 6, 7, 8. Let's back time down a little bit. Getting pretty close. And we want to leave ourselves enough time to get up into orbit. One thing I want to figure out real quick, just give me 1 second here. Time ahead, and we just need to get everything dialed in, because obviously the eject orientation that we established yesterday is no longer valid, even though it's really not that far off. And we really won't even need an hour like I thought, because we're not going to go... The reason I wanted an hour, because I figured if our eject, or if our launch date was over, if we were going to launch from this point and have to go all the way around, we would need close to an hour, but since we're launching here, it looks like we're only going to need maybe 25 or 30 minutes. So let me go back here and let's go, just go forward another. Okay, welcome back to the next part of the video. In the last video we got ourselves all fueled up and ready to go. We've got all the locks that we need to make it all the way through the mission, and we did a few basic calculations to make sure that we would in fact have all the fuel that we needed for the entire mission. So now we're ready to fly, but what we got to do here first is we need to get closer to the launch date, because while we were setting up our plan, we decided that we would leave 1 day later than we actually set up. So let's go to stage 2 here, and let's get a look at when that eject date is. That's 5794.13